Hello and welcome to this presentation on airborne wind energy. This is from Windswept and Interesting Limited, and I'm Roderick Reed. This presentation was originally given at the Airborne Wind Energy Conference in Strathclyde, and unfortunately the videos that were recorded at that conference weren't deemed of high enough quality to reproduce. So it's lockdown 2020 just now, and you see I've got the terrible haircut. So I've got time now to go over this video again and go over this presentation and let you know about another type of airborne wind energy. So at the conference there was talk that there's a fair bit of convergence in the designs in airborne wind energy, and I think possibly that's misrepresented in that mostly it's been yo-yo systems, pumping kite systems that are talked about. Now this is a very different strategy of working out airborne wind energy. It involves networking multiple kite units together. And so we'll go over that here. You see various examples. I've got a soft one working, a broken one working, one out in public, another one in the background. And we're going to talk about the scalability of them as well. So let's have a little look. This is what they look like when they're up and spinning. You can see the fairly rigid blades on a fairly soft shaft there. And this is just outside the house here, just around the corner. And yeah, it's a very simple setup. So let's go over what that is. The main things to take away from this presentation are that these designs are homemade. They're very simple. The scalability of these designs seems to be very good so far. And they're really safe. Mostly because of the simplicity and partly to do with the networking. So we'll go over each one of these components. Simplicity, why is it simple? Well, there's no controller in the airborne part, so there's not much to go wrong. These are lifted into the air. You saw a lifting kite at the top. So you've got your rotor there, there's a lifting kite above that. There's, in those they're inherently mechanically in place, so you don't need all those very technical airborne controls that keep having to be improved in order to get anything reliable in the sky. This is mechanically autonomous. They're very simple to build and put out there. I carry the kit out on my own. I can take it out in a car. One of my kids took a set off to Austria and deployed it for a week there. They work in torque. So there's continuous output. Again, that's simple because you don't need the power conditioning systems that you do for other setups. There's certainly the pumping ones. They're also simple to keep stable because networks have a wide tethering topology, and kites with wide tethering are a lot more stable to fly. So if you've got a great big wide bar, your kite in the middle can be held very securely and easily hold position. So you see that, like we say, simple. These are made on some very cheap toys, as you'll see there. The very first one being just an old mountain bike with a motor on it. So stability. Here you see kites with a wild wind vector going over the field. Each one of the blue lines, is tearing it. But now you've got a network tying those kites together, and the individual kites are held much more in position as compared to when the network isn't there. So networkings give you this wide stability, which really helps in performance. Like I say, it's been super simple. There's been some very cheap and cheerful designs along the way. Even just a stick in the ground with a wheel on top is enough for a ground station in this case, because you're looking at a rotary output power. So there's been really simple designs. Okay, so next thing we'll look at scalability. You can stack these designs, so you can put one rotor on top of another one, as you saw in the video at the start. You can pack them over fields, so we can array them under lifting networks, and you can change the sizes as they are live. So you'll notice some of them expand when they're working, and that's important to another part of the scalability we'll look at as well. Another thing you can do is layer them concentrically as well. So there's quite a bit of layering in these network designs. And so with the basic rotor stacked into a 3-layer turbine there. You can multiply that, add it into one of these lifting networks, and end up with a field here where the motors are stacked, packed onto the field, and you can even add them concentrically up the set there. So the scalability is really good in terms of deployment and field deployment, but if you look at the scalability of an individual turbine, so this is looking from the base there, here's the top. We've got these force vectors of the kites, which are very reasonable in their direction. So if we're looking from the side here, there's more lift on the top ones, slightly larger because they're going to be in a slightly higher wind, moving faster, probably a bigger wing as well deployed, maybe more efficient. But you look at the bottom ones, that opened up slightly more. The top ones, more about driving and lifting, whereas the bottom vectors, they're a wee bit more about expanding the set open, so keeping the network open as the whole thing turns around. Now, why is it that way? Well, if you imagine this is purely soft, this inner network, the green material, which at the bottom you can see it goes to a much higher force, goes through to yellow and red. If you have just a soft, like a trouser leg maybe, or some sort of sleeve like that, and you twist it, it's going to compress. The torsion in the middle will make it collapse. But if you have on every point on that sleeve, you have a piece lifting out like a kite, pulling it outwards, then you can expand the size of this soft torque transfer mechanism into something really, really large. And according to the studies we've done, this can be very large indeed. Well, we don't know the limit of number of kites operated on that. That really will probably come down to functionality and how deployment works. And we've got a few schemes in the plans for that. So you see in action, it actually works like this. You see the sort of triangular shapes these rings are taking, and those are rings on deployment. When it starts spinning up, and once you've got the force in the kite blades, those blades are slightly banked down so that they're tending to expand. But there's also centrifugal acceleration there as well as that's rotating round. So that keeps everything outwards. Now, if I'll go back a wee second, we've got the two parts there. You've got the turbine on top, and so that's expanding. But let's look now at the transmission section. You'll see there's a section here of rings lower down. Now, in terms of scalability, this section doesn't have to be that long. It only has to be high enough so that these clear the ground. So as the rest of the thing scales up and stacks on top, that wouldn't have to change. Yes, you'll probably want to go wider as you make bigger systems. That really helps with the force transmission. Also, you don't want a large gap between the rings on the way up. It's much easier to transfer torque between shorter gaps. And that's what these studies here have been showing, that we've got for a certain ratio of ring size, ring diameter to gap between the rings, it's much better for compression on the elements. If you've got a large ring and you've got a short gap, it kind of makes sense really that you can transmit. But there are, conditions where you will be able to make these things fail. So under extreme loading, that will happen. This is 168 kites on one soft shaft here, and there's a whole lot of very fast-forwarded beam compression simulations that we worked on in order to work out, as we scale up, what are the needs of these systems. And so we've been doing a bit of charting, and we reckon we're getting somewhere on the scaling on that, and it's looking good. So safety. Right, I'm going to show you what happens when these things break, and this is probably the most interesting part. We've been doing FMEA and stuff since the conference and working on improved models, but here back in October 2019 we'd had a few tests before we went out, and here's 3 situations where the system had issues. Okay, so in this one, this was the first one that happened. 7 lines here twisted together, the whole shaft over twisted because of poor control in the ground station, and those 7 lines broke. That sounds catastrophic, apart from, you'll notice here there's a back line and nothing actually broke away. So if you've got a pumping line system or any of your standard drag mode kite setups, a line break is catastrophic. Here, 7 lines broke and nothing broke away. Everything stayed absolutely connected to ground. So that's a definite safety mechanism there. And again, you can see the back line coming into use on this bottom right picture here. There was an over twist due to the ground station being insecure in how it was tracking. So normally I've got a couple of sticks bunged in the ground to help with that, but we're again working on a better system for that. But you see the back line is very handy for bringing the rotor to stall. You can bring the rotor out of plane of the wind, and when it comes round, it'll stall as it's side on to the wind. It's also very good for launching and lifting and recovery options. In terms of a large network, you can either deploy up the lifted lines, the type of lift networks you saw earlier, or you can have back lines, side lines, other lines, have the whole lift network come round out of the wind and drop things up and down that way. Here's the plan. The third one here on your left, you'll notice there's 3 broken parts here. This was spun up too hard, and basically the design was too weak at the back of the fuselage. So you'll notice behind each of the fuselage join points here on the rings, there's been a snap in what these rods were, yet the whole thing is still going round. Now we've had lines snap on various parts, multiple lines snap, and the whole thing still works before. So you'll notice degraded performance if a piece does break. And so at this point, we weren't taking full power out of here, but we still let this run. And you can see the wing loading on these wings here as it's still winging around. So there's various ways to take this forward and optimize all these systems and work and stuff. And so we're looking at whole ways to improve it, a whole bunch of ways. And yeah, there's a lot of good stuff to be said about how this can be done, where it can be done, and it's got a lot going for this system. So yeah, there's the main takeaway. Network kite systems are simple, scalable, and safe. Networks really are, they really bring advantages into airborne wind energy. So yeah, that's the presentation for AWEC 2019 out at last. Okay, thank you very much.